Okay, so C. How do we do it? How do we find the sum of the roots? Like these are our roots here, right? How can we add them together?
Would you do the alpha plus beta plus
Ooh.
gamma thing?
Yeah, what do you do?
But then that'd just be B on A.
Oh, okay. So, actually, well, what's our polynomial, I guess? Minus A, right? Oh, yeah. Would that work? Let's try it. So something like this, I suppose. And then what's minus B on A? That would be 0. Okay. So that would be the product of roots. And what's the sum of the roots? The last one, hey? Yeah. So negative D on A is equal to 8I over 1. It's an interesting thought. Well, we can try and verify this, hey. The other way we could do it is we could take these guys here individually and add them up. So if we take 2EI pi on 6 and 2EI 5 pi on 6 and 2EI negative I pi on 2. Now, looking at this one, this is not something you can put in your calculator straight up, right? Even my FX100 even though it can do complex numbers, for some reason they couldn't add these up here, right? So let's have a look. And when I think about these here, this is not something I really want to be adding because I can't really add the exponent. I can't add these sort of exponential functions together very easily, at least, right? So, is there another way we can write these? We have a few different ways.
Yeah, it seems form to like polar or something.
Yeah. So the cos I sine theta form. Just so important to know because I see you guys mentioning it. This is technically kind of like polar form anyway. It's just in the they call it like Euler form or something like that. But it's polar form because you've got a modulus and an argument written there, right? But yeah, if we converted this to the cos I sine theta form, right? We had cos pi on 6 plus I sine. This might be a bit easier to do because this one now you can't actually calculate, right? In fact, we could take out 2 from the whole thing, but let's just leave it like this for now. Yeah, look at that. It's convenient that they do that. And typically they'll do stuff like that with these kind of questions because they're a bit easier to calculate rather than giving you, weird radians that you'll have to deal with. They may do that from time to time, but it is quite common that they'll do these nice exact values for you to make the calculations a bit easier at least. And we'll see whether this theory holds true. While I look this up. How'd you go? What do you get?
Well, the 2 cos.
Yep.
2 with bracket
Yep.
3 on 2.
Mm-hmm.
Plus I half.
Yep.
And then we have 2 and then that one would be.
That's right. So I guess maybe use this as your unit circle kind of thing as well, because the reference angle is the same for this one, but then it's in the sine quadrant, hey?
Yeah, so it's minus.
Good, yeah. Yeah, and that's going to actually help us a lot you can start to see how things might cancel out, right? So still positive though for this one. Yep.
And plus 2 cos negative half.
Yep.
Is 0.
Yep. Just thinking.
Plus negative 1. I negative 1. So negative 1.
Yep, easy. So then let's just put these all together. We can start to see stuff that's going to cancel out, right? Like this one and this one. Then this is going to be leaving us with, what's that? That's just I plus I minus 2I. Yeah. Well, that's nice, isn't it? And that actually equals to 0. So this is something that we'll prove a bit later on, but the sum of our roots for a complex number is actually always going to be 0. Okay, so the sum of all the roots in a complex number will always be 0. So I'll formalize that for you here. We won't prove that right now, but I will write that out here. So the sum of the roots is 0. Let's put that over here. The sum of the roots Okay, so that's a property that they like to use a lot of the time for you to solve various problems. Going back to this though, I couldn't find anything just for now. I will come back to it. What Alyssa suggested, could you use the sort of theorems that you've used in extension 1 for those polynomial expressions? Didn't look like it quite worked. Oh, was it? Oh, maybe. Oh, maybe. I'm sorry. Maybe I'm wrong then. Yeah. Maybe.
I don't know which way around.
No, you're right. Sorry. Yeah. So actually, the product of them multiplied together should be 8i then. Hey, should we check that?
Well, it is.
Oh.
Z cubed equals 8i.
Oh yeah, of course. Yeah. Wow. So it actually does work. So these theorems do work. So we can test out, and in fact, we don't even need like all this kind of stuff. We can actually just find the sum of these all together and using our theorems there. So that's pretty cool too. Sorry, I didn't catch that one. Cool.